All right. So here's the thing. You know, when you give a speech, you should always have a personal game. And my personal game today is how many times I can say the word super. So I am super happy to see all y'all. Super happy to see you guys. So you know what I want to do today is I want to give you a perspective, our perspective on what's going on in HPC. I want to tell you what I've been up to in the last year, some of the work that we've been doing, and where we think that's going to lead us. The last 15 years, this just came out today. I love studying these charts. You guys, this is just the most fantastic thing ever. And so if you take a look at the last 15 years, something remarkable happened. In the last 15 years, there's basically been one way to build supercomputers. The usage of commodity CPUs was so prevalent for a very important reason. The R&D budget, the pace of innovation of building commodity CPUs, dwarfed the entire combination of just about every supercomputing innovation out there. It was nearly impossible, it was basically impossible, to out-innovate this incredible engine called the CPU. Its performance per node was excellent, its functionality was excellent, and quite frankly, its price was excellent. That way of building clusters, supercomputing clusters, out of combining networking a whole bunch of commodity CPUs was a fantastic way to build supercomputers. Well, a lot of things are about to change. I think you guys realize a lot of things are about to change. We believe a lot of things are about to change. Whether Moore's law slows down, ends, or otherwise, it's utterly irrelevant at this point. It is very, very clear that we have to look for a new path forward, new approach forward. And just about everybody is looking for a new architecture. Here's the interesting observation, though. Over the course of the last 15 years, it is arguably very, very difficult to make an architectural decision about a supercomputer and be off by a factor of anything significant. However, for the first time in 15 years, it is actually possible to design a supercomputer where the throughput could be off by a factor of 5x. There are very large decisions to be made. There are many options, and surely many of you are looking at them. Our perspective is that the approach forward is accelerated computing. We pioneered accelerated computing. We are all in on accelerated computing. Now, this chart shows you our perspective, how we look at accelerated computing. There's a couple of things to highlight. The first thing is this. The only way to keep up with a commodity, and when I say commodity, I don't mean inexpensive. I mean commodity means there's a large market for it. There is a very large day job. There's a fundamental reason for its existence. There are enormous number of opportunities and markets for it. Commodity is a very important technology underpinning. In order to beat a commodity, or if you will, accelerate a commodity, you have to use another commodity. The reason why we believe that GPU was the right way forward is because there's a day job for the GPU. There are large markets that needs the GPU. The rate of innovation of a GPU is incredibly high. We have the ability to invest well over $1 billion a year, and at this point over $10 billion of total investment into the GPU to advance this form of computing. So number one, in order to be a companion to a very powerful, very fast commodity, you have to also be a commodity yourself. And that's one of the reasons why we decided to use the GPU. The second thing to observe is this other companion processor has to have a unique value proposition. Its design approach has to be so fundamentally different that it can engage certain classes of applications and accelerate it in a way that is impossible otherwise. You cannot be a general purpose processor. You have to select your applications. And so the second observation is we observed that using a GPU that is inherently great for parallel processing, if combined with a strong CPU, We can accelerate a large range of interesting applications we select, and very importantly, never do harm. One of the things that's really important about accelerated computing is the worst case scenario is a speed up of 1x. Amdahl's law still applies, and when you create a completely different architecture, too much of the code is set back for you to make up with the part that you accelerate. And so the first part of this chart is simply why we believed GPU is going to be can be a companion processor for a very, very long time. Now, one simple observation is, in the workstation industry, in the gaming industry, the GPU has sat next to the CPU now for 25 years. We've been accelerating applications for well over 2.5 decades. My sense is at this point, we see a path forward to many decades to come. The second part of it is this. We believe that ultimately a great computing platform is all about developers. If the developers don't have a productive computing environment, a productive programming environment, you just have a bag of chips. That was funny. Bag of chips, guys. A super bag of chips. Come on, you guys. We're in a conference. All of you guys are intoxicated. Everybody's out there drinking except for me right now. So we could be funny. All right. So the second thing is recognizing that the programmer, the developer is the most important thing. Creating a robust environment for them. This environment has also some interesting characteristics. One, don't forget what a computing platform is. The applications you develop today has to be productive tomorrow when a new processor comes along. It has to be forwards and backwards compatible. And one of the things that we're really proud of is now CUDA is in multiple versions. The GPUs underneath have introduced features after features after features, but yet they're fully compatible from generation to generation. The third, co-design. One of the things that's really special, and it's a unique advantage of accelerated computing, is observing that you don't have to accelerate everything. You have the ability to pick and choose. You don't have to accelerate everything because there's already a strong CPU backing you up. You don't have to accelerate everything. So the things that you do accelerate, you could accelerate the living daylights out of. And the way we think through it is simply this. We target the applications that are of great importance to you, the applications that consume a large proportion of the workload of a data center, applications that we can uniquely accelerate, and we think about it from the processor architecture, the processor design, the system software, the system, the middleware, all the way up to the application. We're one of the few companies in the world that has the ability to think along this entire path, integrate it all, accelerate the application, and not only that, apply that learning to next generation GPUs. That's one of the reasons why the work that we've done with you over the years has continued to accelerate at a pace arguably almost unreasonable. Almost unreasonable. And so it's not unusual to see a speed up of many times from generation to generation. And it's because of this holistic approach of co-design. And then lastly, no computing architecture is useful if it's not accessible. If developers can't get their hands on it, if not a large body of work can be developed on it, the platform simply will not become more valuable. Our perspective all along is that the GPU has the ability to do this because it has a day job. And that day job can carry CUDA, can carry our programming architecture to far corners of the world so that every application developer can access it. Everybody has access to a PC. Everybody has access to a GPU. If you would like to have a personal supercomputer, this is the way to do it. But we've taken it much further than that now. We've put GPUs in the cloud. It is in just about every major cloud platforms in the world. We've, of course, continued to innovate in PCs, and CUDA is available on all kinds of GPUs, all kinds of GeForces. And of course, we recently took CUDA and we shrunk it down into a little tiny module, into a little tiny supercomputer, little tiny super embedded computer. And so our perspective on accelerated computing are these elements. One, a commodity that has the ability to continue to innovate at a pace that can keep up with a strong CPU. 2, a programming environment that is productive to developers, that provides for forward and backward compatibility. And as the body of work continues to grow, your platform becomes more and more valuable. 3, a holistic approach to thinking about applications so that we can accelerate your applications beyond the transistor performance would suggest. And 4, ultimately, it's about accessibility, putting the platform in your hands. Well, the results are pretty compelling. In fact, I would say that this year was a major change year in how we think about accelerated computing. There's not one person I've talked to who isn't seriously considering or have already broadly adopted accelerated computing in some way. Over 100 systems in the top 500 are now accelerated. Of the last 24, the latest 24 accelerated systems, 23 of them are Tesla. A third of the total flops of high-performance computing, of supercomputing, is now accelerated, and we're growing at effectively 50% per year. This is pretty amazing. Thank you, guys. I really appreciate that. And this is, I believe, indication of our dedication to this platform, our dedication to this method of computing, and our dedication to all of you that are developing on it. There's a second thing that's changing. There's a second thing. Of course, the first thing is, wow, supercomputing, the architecture is going to change and change in a big way. The second thing is the application of supercomputing is going to change in a big way. You guys know this very well. The #1 killer app for consumers today is a supercomputing app. The work that you've done, the advances that you've made, the road that you've paved has made it possible for us to apply deep learning techniques, machine learning techniques, to enhance and make more wonderful consumer applications everywhere. Machine learning, this field of computing that we've been working on for the last 4 or 5 years, plugging away at it, working on ways to accelerate it. All of you probably heard about cuDNN, the work that we've done in machine learning. The results are now starting to flood out to the marketplace. Just last week alone, Google announced that they open sourced TensorFlow. You can see CUDA code all over it. Just last week, shortly after, Microsoft open sourced their machine learning app framework. You could see that the applications are also pretty amazing. Microsoft said that, in fact, using machine learning, your next generation Cortana, which is a digital assistant, may very well replace the browser. It can be that smart and that wonderful. Whether it's photo applications that appears to do things and sort and find in a way that surprises all of us and just looks like magic, okay, to other applications that are now starting to sweep through cloud services. Machine learning is in the process of going from R&D into deployment. This is a very, very big deal. Our strategy has been, of course, #1, to enable the developers. The developers in machine learning started with research and started in many of the universities that you guys are part of, started in research using high-performance computers in the form of a GeForce. They used GeForce supercomputers, if you will, to create their machine learning discoveries, which then led them to working at major companies like Google and Facebook and Baidu and others. Their work is now emerging from R&D and going into production. We introduced a Tesla accelerated computing platform dedicated to machine learning recently. On the one hand, it's a processor that is the most powerful processor you can imagine for machine learning, so that we could reduce training times from weeks to days. And on the other hand, a very low power, very, very energy efficient processor, Tesla processor, for inferencing, so that these billions of searches, these billions of videos, and trillions of hours of user-generated content has the opportunity to be processed very efficiently by these Tesla processors. This is our new Tesla accelerated computing stack. And so that's the second thing. The second thing that's changing in supercomputing is a brand new class of applications. A second thing that's changing in supercomputing is for the first time, supercomputers, high-performance computing techniques are now going into consumer applications. We're seeing them in industries. This method of computing is wonderfully rich for all industries, from life science, medical imaging, financials, all kinds of interesting applications that we're starting to see all over the world. It is also, as many of you know, incredibly helpful to high-performance computing itself. And the reason for that is this. Although the web services, the consumer web services, get a large amount of content from users, you generate an enormous amount of content in your simulators. That content ultimately, that data ultimately, is there for you to find insight. The discovery of insight is a big data analytics problem. Supercomputing is ultimately, if you will, the mother of big data. And so I think this is going to be a technique that's going to be of great importance, and supercomputing now has a brand new vector for growth and innovation: big data analytics, machine learning. Now here at NVIDIA, what we're going to do is we're going to take supercomputing techniques and machine learning techniques and apply it to all kinds of interesting other platforms. One of our favorite platforms, one of my personal favorite, is the car. Everybody needs a better car. And all of us engineers ought to dedicate ourselves to build our own toys. And one of the areas of great innovation is, of course, the self-driving car. Not only is it going to be wonderful for society, it's going to be wonderful for our energy, it's going to be all kinds of wonderful new safety benefits. We're seeing autonomous driving capability emerge in two different ways. One, of course, better cars that are safer to drive. And the second, services that will literally revolutionize the car industry altogether and turn transportation into a service. Helping cars drive by itself has three basic functionality, three basic components. One, you have to detect the world around you, a very complicated machine learning problem. The world thought that using computer vision techniques, handwriting algorithms was the way to make that possible. It is very, very clear now machine learning and artificial intelligence is a superior method. The second thing, you have to localize yourself, figure out where you are in the world down to a few centimeters so that you could, from that point forward, navigate. And then lastly, path plan. If something were to happen in front of you, you have to find different paths and different alternative routes. These capabilities, these functionalities, as you know, are supercomputing functionalities. We're going to put supercomputers in the car. Very quickly, the way we bring this capability to the marketplace, on the one hand, a workstation, an appliance that is designed for one singular purpose: design and help you program, help you train your network as fast as humanly possible. And then number two, when you create this network, you put it onto a little tiny processor, the Tegra processor, which is now part of the Drive platform. This network allows you to inference, detect, localize, and plan, help you drive your car. One of the things that's really amazing is this. This is the power of deep learning. This is the power of machine learning. When we first introduced the idea, I'll just tell you, flat out, 100% of the car companies we talked to felt it was not a good approach. And the reason for that is because at the time, computer vision approaches were already detecting cars and objects at 85% levels. And machine learning was a little bit of a fantasy at the time, and it was really hard to quantify how good it can be. Here's the powerful thing about software. If you have a great computing platform that you can iterate quickly on, and your body of work continues to improve, that iteration methodology, fast iteration methodology, is arguably hard to beat. Look at the rate of improvement of NVIDIA's network. It is now the second most accurate real-time driving network in the world. We call it NVIDIA, the NV DriveNet. We're not ready to share with the public yet, but hopefully by early next year, if you're interested in building a robot that runs around by itself, you could take advantage of the NV DriveNet. We think that cars are going to be powered by supercomputing technology and machine learning technology. But we think that just about everything is going to be powered by supercomputing and machine learning capability. Could you imagine if you could talk to a robot, tell it what to do, fetch a ball, watch my kids, go walk my dog, all of those kind of wonderful, fun things. You could imagine robots that could be of great assistance. Drones that never run into each other again. Drones that knows where it is. Drones that can navigate around. And drones with cameras and microphones and speakers so that you could arguably have virtual presence. And then lastly, little devices around the house, whether it's smart cameras or otherwise. Instead of recording everything, it only records the smart things. It detects the smart things, the things that are of interest. It recognizes who you are. It could tell you stories. Machine learning, artificial intelligence capability, powered by supercomputing technology, is going to sweep the landscape. I think this is going to be a really important thing. And so we built a little tiny module. This is the world's smallest supercomputer. It is 1 teraflops. It is 1 teraflops. You guys probably remember when 1 teraflops came along and what it used to look like. In fact, it probably used to, in the early 1990s, it probably used to take up a whole basketball court. So 1 teraflops of supercomputing capability, but here's the really wonderful thing. This is architecturally exactly the same as the supercomputers that have Tesla in it. It is exactly the same CUDA. It is exactly the same framework. It is exactly the same architecture. And so all of the software programming, all of the investment around this platform carries over so naturally. And so that's it. That's the third thing I recognize, I observe, and would like to share with you with respect to supercomputing. Supercomputing technology is in the process of extending well beyond supercomputing. The work that we have done together, the advancements that we've made, is in the process of revolutionizing consumer applications, cloud services, the automotive industry, autonomous machines, and bring joy to countless people you can't imagine. 2, the architecture of supercomputing will change. The energy efficiency that we need in order to support supercomputing everywhere, the acceleration that we need in order to provide for simulation and machine learning and data analytics for this new generation of problems, both require a new architecture. We are all in on accelerated computing. Are you guys with us? All right. I'm the warm-up act for Ian Buck. Ian Buck, how'd I do? I said the word super 74 times. With that, super Ian Buck.
Thank you, Jen-Hsun. All right, hopefully you guys can hear me. So I'm gonna talk a little bit more about our news here at Supercomputing and the progress that we have made. I think it's important, as Jen-Hsun described, our Tesla platform is it's really about 3 things. First, of course, it's about simulation of all the work of the science that's been done on GPUs today. Second, it's about machine learning. And I think Jen-Hsun showed you all the amazing things that are going to happen around machine learning. I'll talk a little bit more about that. And I want to highlight a third one, which is really important. As our science gets bigger, it's also about the visualization, being able to see our results, interact with them, and engage with them, all being done on our GPUs. The adoption is clear. I think the top 500 makes it very clear. There's a new report out recently that found that in a survey of the top supercomputing sites, 1/3 of them today are now equipped with accelerators, and half of all the newly deployed systems are now accelerated. So, I mean, the trend is really obvious, and it really speaks to the work that we've done here and the work that you guys have done. So, thank you. 70% of applications today are now accelerated. This is you can't do your science unless your applications can run and get the benefit of GPU acceleration. This is the result of a recent survey. They found that 9 out of the 10 top HPC applications can support accelerators, and 70% of the top 50 applications are now accelerated. So the adoption is very clear, and the momentum makes it obvious. The one that we're happy to announce here today is VASP. VASP is a material science code. It's used to understand why materials work at the atomic level, why a battery is only so efficient, why wires do what they do, why plastics do what they do, why metals do what they do. VASP is now, that this conference, number 9 of the 9 out of the 10 that now is GPU accelerated. It consumes about 10 to 25% of CPU cycles on supercomputers worldwide. So we're really happy to with our partners in VASP to announce its adoption. We have over 370 applications that are now GPU accelerated. So we have a full catalog here. I think we have it here at the show, and you can take a look at it yourself. But the adoption has been great. So let me walk through the 3 segments and explain how we help people get onto the Tesla platform. First, Tesla for simulation. Again, this is about developers, giving them the right tools to get the benefits of GPU acceleration. And it comes in 3 forms. First is libraries, whether it's BLOS, FFT, Thrust, cuDNN, all sorts of libraries. The easiest way to get onto the GPU. Directive approaches, which we first talked about here at Supercomputing a few years ago, now continues to drive forward. We're on version 2.5 of OpenACC, and I invite you to check out the demos here at Supercomputing. And of course, the effect that we've had on programming languages in general. Started with CUDA and driving in C, C++, and Fortran, being able to directly program the GPU like any other parallel processor. All of this is packaged up in our accelerated computing toolkit, available for our website. We've had over 3 million downloads of this toolkit since we started back in 2007. So it's been amazing for us. Our flagship GPU today is the Tesla K80. It's all about performance. For an application like Amber, which does molecular dynamics, it's taking simulation time down from a month to a week with an enormous amount of performance. It's 1.9 teraflops of double precision, 2.9, so 24 gigs of memory, an incredibly fast GPU, and most of the centers today are deploying with Tesla K80. Even a partial deployment of GPUs in data centers delivers amazing value. If I look at some of the applications listed here, LAMPS, Chroma, NAMD, Amber, we're speeding up these applications by 5, in some cases almost 15x of performance. Just deploying a third of the nodes with GPUs is doubling the throughput of a data center. This means more science, more data, more simulations are pumped through every day with even just a modest deployment of GPUs in the data center. And of course, programmability. A few years ago, we introduced OpenACC with our partners, with Cray and Pascal, PGI. The important announcement of directives is that it lets developers program at a high level. You can take your partial differential equations, write the Fortran code that explains them, and then provide simple hints in terms of comments to the developer, to the runtime system, and let it map the calculation to the architecture in the right way possible. The programmer doesn't need to program the architecture. We let the compiler and the runtime do it for you. Here at Supercomputing, PGI is showing performance portability with OpenACC. For the first time, we have the same code written in these examples, the same code, the same directives running at peak performance on a CPU and a GPU, totally unmodified. So whether or not your application runs on a CPU-only system or a GPU-accelerated one, you're going to get the best performance. You're going to get performance portability. It's a language and a solution that you can invest in and see those returns for a long, long time. Jen-Hsun talked about machine learning. It's a very important field. We have new GPUs for that market and also new software to engage. The Tesla M40 for training, the M4, its little brother for inference, and of course all sorts of software on top to enable the hyperscale data centers to deploy their services on GPUs. For training neural networks, it's all about time to solution. How quickly can you train a network to view its results, understand its performance, and kick off another experiment or deploy it in a data center? A Tesla M40 can take a training time from 8 days down to even a single day of training time. That means you get really rapid response in your machine learning training to get the high accuracy you need for deployment, to get up to the 90-92% accurate. It's a Maxwell-based GPU. It's got over 3,000 cores and 12 gigs of memory. An amazing, amazing GPU for training neural networks. And then its little brother, a new GPU for us, is actually the Tesla M4. The hyperscale data center, the open compute racks, these servers are very low power, 300, 400 watt. This GPU is actually a half-height, half-length GPU and runs and delivers performance with only 50 to 75 watts of power. It gets all of its power through the PCIe connection. Despite its small size, it delivers a lot of performance in 4x in video processing, image processing, transcoding, and machine learning inference. It is the GPU that can offload all these heavy compute workloads in the hyperscale data center, take it off the CPU, put it on the GPU, leaves the CPU free for all the web serving and Hadoop jobs that are not GPU accelerated. The last part of our solution is visualization. It's really, as our scientific simulations are getting bigger and bigger and bigger, we need to visualize the data. It's almost getting too expensive to store all the intermediate results and do post-processing. People want to do in-situ visualization. Actually, while you're simulating, create the visualizations and interact with the simulation in real time. For this, we have 3 software packages. One is called iRay, which is a photorealistic rendering solution that actually see what a product looks like in simulation, accurate to the actual materials that it will be used with. Optics is a ray tracing engine, very popular in supercomputing. I have here a picture from John Stone, his software, rendering the chromatophore molecule, a very important molecule that's responsible for photosynthesis. By using ray tracing on the same GPUs that are doing the simulation, John can interact and see the results of his science and visualize it in a photorealistic way and understand the shapes and structures. And finally, Index. Index is a real-time volume rendering engine. It's used for volume visualization, whether it be seismic processing, understanding what's in the ground, or weather and cloud simulation, where you have 3D volume data. These 3 tools give you both photorealistic rendering, real-time ray tracing, and volume visualization, so you can both simulate and visualize your science. One of the great uses of visualization is actually in weather. And weather is a field that's been growing increasingly higher and higher demand for cycles. We've had 2 supercomputers deployed that actually have decided to go with an accelerated approach because of the increased demand for computing and weather simulation. The first is the Mateo Swiss supercomputer, which was announced back in September. Their goal was to increase the accuracy of their daily forecasts and long-term forecasts, and to do that they had to increase their resolution by over 2x. And the other announcement, which actually was just made this morning, was that the next generation NOAA supercomputer, the weather agency responsible in the U.S. for weather forecasting, will be deploying next year their next supercomputer to design their next generation weather models. Same problem. They need to get down to a finer resolution to accurately model the track of thunderstorms, hurricanes, tornadoes, climate change, El Nino. The old adage is true. If you flap your butterfly flaps and swings, you're going to get storms in China. You need to simulate those small effects to understand what the macro effects are for the storms and the weather patterns. They're going down to a 3-kilometer resolution. That's a 5-fold increase from what they have today, which requires over a 40x increase in the computational complexity of their models. All this is happening in 3D. On top of simulating it, you actually want to visualize it. So we actually have, these are actual real visualizations of the actual simulations using the Index software, so you can see and track the storms as they move through the simulation. And of course, all this is driving the next generation of supercomputers to be GPU accelerated. For simulation, I can't point to a bigger supercomputer than what the US government's doing with their Coral initiative, the Summit and Sierra supercomputer, which was announced last year here at Supercomputing. For machine learning, it doesn't get any bigger than IBM Watson. This morning, IBM announced that the Watson machine learning platform is GPU accelerated. They're able to make Watson 10 times smarter by deploying machine learning on GPUs. And we have some Watson demos here at the Supercomputing today. And of course, visualization. NOAA, and all the weather, simulating doing the simulation and also visualizing an important part of where HPC is going. So with that, I'll adjourn. I do want to invite you to explore our booth. We have some amazing demos here. Around the corner here, we have the Mateo Swiss supercomputing streaming a weather simulation live from Switzerland across the world to our booth, to that monitor right there. You can watch a real-time weather simulation across Switzerland and being rendered in real time with the Index software. We have a nanowire simulation. This is one of the Gordon Bell finalists this year to understand how electrons flow through tiny, smaller and smaller semiconductor devices that may be measured only in atoms instead of nanometers. Understanding electron motion in these tiny, tiny wires is really important for next-gen semiconductor technology. This was a 19 petaflop supercomputer run on 10,000 GPUs on the Titan supercomputer, and it's actually using optics to do all the rendering. In addition to that, we have a tornado simulation of a real, actual tornado that hit Oklahoma back in 2011, rendered with Index and interactive in real time. And finally, our friends at IBM are demoing the GPU-accelerated Spark. Spark is a data analytics language and platform which is used widely across the industry to process big data. IBM's now made it GPU-accelerated, and they can show you how that performance turns into real results through a predictive medicine application that they have showing here at our booth. So with that, I welcome everyone to supercomputing. Thank you for sticking around, and enjoy the rest of SC15.